Well, let's see how this works. Let's try a couple examples of the natural log rule and just see how it rolls out. Each of these are situations where you might have something a little more than just the natural log of x. So if I'm trying to find the derivative here, once again, you take the reciprocal times the derivative of 2x. Now this will simplify, and you get a nice little answer of 1 over x. And you say, gosh, that's not too hard. But I did want to stop and show you one little thing about this. If you can simplify these logarithmic expressions first, it's going to make your life a little easier. In this situation, it didn't make any difference. It's not going to matter. But in a lot of the harder ones, it might matter. If you use those rules about logarithms that you had learned previously, either the product rule, the quotient rule, or the power rule, you know that before you even take a derivative, you can rewrite that logarithm. Since 2 is multiplied by x, I can write it as log of 2 plus log of x. Then when I go to take the derivative, I know that the derivative of any constant is just 0. Therefore, this is just the same as taking the natural log of x. I'm going to use that same idea to number 2. Number 2, which would be a lot harder if I tried to say 1 over this cube root times the derivative of that cube root. I think it's going to be a heck of a lot easier if I just use that power rule. The rule that says if I'm taking the log of something to a power, I can move the power up front. Now when I go to take a derivative here, oh, it is so much easier to just say, you know what, I have that coefficient 1/3. I will take the reciprocal of what's inside my log times the derivative of that log, x plus 4. And I finally come up with a final answer that looks just grand. Okay, so once again to recap, I could have taken 1 over the cube root, but then when I take the derivative of the cube root, that's kind of a pain. If you can simplify how you write these. Same thing for example 3, I've got 6 times the natural log of x. I think it's going to be real easy to spot this one if you do it the right way. That is really just 6 times the natural log of x. So please simplify first. Just to show a counterexample to that, please realize number 4 looks very similar. It's to the 6th power, it has a log, and it has an x. However, that is not the natural log of x to a power. That is equivalent to the entire logarithm to the 6th power. So when you do this, please use all the chain rule knowledge that you have acquired already. We realize that this could be written out as y equals u to the 6th and u equals the natural log of x. Okay, I'm going to kind of shortcut this and say I'm taking the derivative of my outside function times the derivative of my inside function, which is what I would get if I took the derivative of u to the 6th and the derivative of the natural log. Am I done? Well, pretty much. That's a nice way of writing it, and hopefully that works out pretty well. Finally, even when we get to something a little bit weird, like trig values, it's not a big deal. We still are going to take the reciprocal of that logarithm times the derivative of what's in that logarithm. Please don't forget all of your special rules for your derivatives. Make sure every day review some of those rules, and you will never be left wondering what the derivative of cosecant is. There's 5 straightforward examples, and we might have a little more with some special examples.